I can tell you the result should be goes to infinity. Basically, the system won't be able to, okay, I can tell you the result. If you do the calculation, the statistical error should be very large, very large. What that means? That means the system's dynamics is too slow to follow up such fast changing input. So which means the input is changing, the input is varying in time too fast. The system response is too slow to catch up. So it's always falling behind. So gradually it's losing out of control. So that means it is farther away from the value of the input. So basically is this error, statistical error goes to infinity, which means just like if you run marathon, if you run with, compete with, if you have seen, watch the YouTube, watch the Berlin, the very famous marathon like Boston, Chicago, New York, Berlin. And the elite runners, basically they are leader group and they always be the focus of the camera. And the funny thing is you've seen sometimes, many times, the audience or the people's on side of the street and try to encourage runners, but always some kind of the funny boys, and try run. You can see they try very hard to run very fast, try to catch up the elite runners who has been running for more than 1 hour. But they can see the boys try to run very fast and very hard and catch up the speed. Only for less than 1 minute, 40 seconds, they're falling down, falling behind. The elite runners still keep the same pace running, and basically I think they run complete the whole thing. Right now the record is 2 hours, 2 minutes, and how many seconds? Basically is you have to run more than 21 kilometers per hour to achieve that result. If you have any chance to go to the SRC on the treadmill, you can put the buttons, and I think 21 kilometers per hour is about 13 miles per hour. You can give it a try. And remember, hook that kind of safety clip on your body. Okay, if you really drag behind, and then just can have the machine to stop you. Okay, but anyhow, that is what I mean. So here, if the system like the general people, and they running very slow, and the input command, for example, is the elite runner of the marathoners. So here we can see they gradually fall behind and distance getting farther and farther. So that means that basically here we lose the control. Okay. If I'm right, I didn't do the calculation, but I believe this is should be the out of control. So this is for the second type, and the third one is parabolic input. For the parabolic input, this one is the system dynamic is even faster. So that is this. So this is parabolic. I think I have a typo here. So parabolic input, you can see the change of the input in time is even faster than this one, right? So this is a very fast the command input. So if the system wouldn't be able to catch up the linear input, then we don't have to mention this one. Will be even fall behind. So if the previous example will be blown up, which means the sense error will be infinity, therefore this one could be the infinity to the double degrees. Basically it's infinity. Okay. And here I have a mistake. This should be, if the t square is the RT, the Laplace transfer should be how much? 2. No. This should be t squared divided by 2, then that corresponding is this one. So if that one, yes, I think you're right. This should be 2 over s squared, s cubed, yeah. So the numerator here should be 2. if you have printed out the handouts here, please modify here. I will correct this one. So here the 3 pages basically showing is the aerodynamics, the steady state error calculation for general 3 kinds of the inputs. And here we have the unit step input here. So those are the 3, and if you wish, we can add one more. So here is the unit impulse. So the 4 are pretty much common, I would say, the test input signals for testing the response of the system. So here, by you might asking why bothers about the calculating the steady state error, and that is a way we usually do the system ID, the system identifications. System identifications usually come up with a few kind of general steps. The first one is we want to know the system is fast enough or not. If the system is fast, which means the system response will be fast enough to catch up, to follow any fast changing command. So we want to define the system dynamics, say, if the system will be able to catch up the unit step input without any steady state error, okay, so then we can say the system at least is this kind of level. Then we will go to the next one. If we give a ramp input, then we found if the system is still able to catch up without any steady state error, then okay, we see the system pretty much fast. Then we will go to the next one. Okay, and that one will give us very good insight into how the system responds. And usually, the linear dynamics, the first order dynamics. Here I'm trying to talk about these. So in terms of your vibrations here, if you have only dampers and only have mass, okay, and if this is the degree of freedom, then this system can be described by mx dot dot plus cx dot. And for example, here if we have any input, so let me say the input is ut. So for this system, although it's second order dynamics, second order degree of freedom system, but I can tell you in mathematics this is the first order dynamic system. Okay, this one, you won't see oscillations. And for this dynamics, you can see it's only decaying. And decaying, this is a feature of the first order. We will see this one more in detail. So for this system, usually we classify as a slow system. Okay, so anyhow, that's kind of give you, try to build up certain mental pictures for learning these things. Okay, so here for, in terms of the aerodynamics, the steady state error analysis, we pretty much have information here. So this slide is, again, this example is from our textbook. So from here, it even give us more constant number assigned here. So again, if we consider this state, the unit, here this is called the unit feedback system, because on the feedback loop, we don't have anything but the gain basically equal to 1. Again, here is a disturbance, and then we also have the command input. So again, we don't consider the disturbance, we just set up equal to 0. Sorry, here should be TD. My mistake, it should be TD. So here we study this, the unit step input, so we put the RS equal to 1 over S. And then we can do the calculations, and again, given these functions, and you should be able to do this by hand for sure, and for the preparation of our test. For example, K 11S plus K, and then S squared plus 12S plus K times RS, okay? So right now we study the system's response to this. So for this one, you simply put into Rs equal to 1 over S. Then you should be able to do the calculation to find the inverse of Ys and enable for yourself to calculate the response Yt. Okay. For this system, it's very simple. Then you must to make sure you know how to do this one by hand. And in our textbook here, provide you the MATLAB command. So for example, here if you pick up k equal to 100, and then if you want to draw the step input, the command is using this one, step. That's it. Step of certain system. The system is defined by numerator and denominator of the closed loop functions. Okay, so here is the closed loop functions, and numerator equal to 11 and k. Again, the arrangement of the numerator polynomial is in the descending order of coefficients in S. So 11k. Denominator is 112k, like this. So once you have this, then you put into TF, meaning transfer functions. In this way, the MATLAB will remember, okay, will recognize this is the system representing this one here. And then step, that means you simply ask MATLAB to provide the command equal to unit. So this is the, I think this is scaled result. So basically this is a response, okay, like this. So here the drawing didn't go too long, but eventually the gap between the input and output should be approaching to 0 as we will calculate it here. Okay. For the same systems, if you like to do the unit impulse, for the unit impulse, then basically Rs equal to 1. Okay. So for Rs equal to 1, then basically Rs here, then you simply make it equal to 1. And then for this one, you should be able to do you should know how to do the calculation of the 1, and then you can plot it. And I forgot what kind of command in MATLAB they give us the drawing of the unit impulse. For this one, once you have the programs being built up, then you can easily change the numbers k. Then you can see the different response very quickly. Okay, and that's the way we do the designing of the controller. And right now, this example actually will lead you to the design of the controller design. Here we have our controllers, and our controller right now in this example only contain one parameter. Basically here we try to tune the parameters to see the response. For different value of the k, I can tell you that the curve will be different. And for example, for different value of k, the curve could be like this. Okay? And so from here you can see if you say I don't like any overshoot, so you may change the k number, so such a curve will be something like this. Okay, so that is the first case. I try to gradually introduce the concept of the controller design. And this controller only have one parameter, that is very easy. And if necessary, we can also put 11 as the special case, special number of another parameter. So here we have multiple parameters. Okay, and if you know the previous class, as a student, in the senior design, they do the wind tunnel, the harvest of the wind turbine, the energy clay. And he told me in his very complicated controller design, basically it only has one parameter. And unfortunately, I failed in teaching him how to do the systematic way to design the controllers, and that's my expectation. I wish I can impose more systematic way in this time, this teaching this time. So, okay. Sorry, right now, up to now, if you I have put some of you into sleep, and sorry, yes.
I was wondering why you don't consider noise and disturbance. Would that affect your response?
Oh yes, yeah, we should, but at this moment for illustration, for demonstrations, we only consider this, don't consider that one. But in fact, in reality, we have to consider both. So consider both, basically we just take the superpositions of the data. And I think in the next few pages. So sorry, my tone make some of you kind of into sleep, kind of do a few seconds, and then, sorry, very sorry for that. And Jason, basically that come back to your questions here. In this slide, here we consider is the influence of this, but we don't consider this one, so you can see. Okay, so if we have a disturbance and is 1 over s, which is very simple, then the response will be like this. And again, for this case, the statistical error of the yt to the disturbance will be 1 over k. Okay, so that is, again, for this slide, right now we consider is the influence of PD to this. So here, this page, we have the two curves ended up together. So this is a curve, this one representing is the influence of our command, and the response will be like this. This will be the influence of the disturbance. The response is like this one here. Okay. And again, do the similar calculation. This calculation is for k equal to 100. And again, if we have MATLAB, we can change k, for example, to 20. Then the response to command is like this. Response to disturbance is like this. Okay. So you can see the response to command, which is the unit step input, that approach to the value pretty quickly. On the other side, the response to disturbance gets reduced. So here from this trend, we see, okay, likely we can take smaller k, will make the things good. Okay. And these slides, let me show you. In our textbook, we have interactive example here. So that is the section 4.8. So those are the figures here. This one. So here is the value of 100, and we...
Your screen's not on. You're blue.
Oh, sorry.
I have a question.
Yes.
So I get that you're superimposing both your disturbance and your unit approach, but if you were to basically sum them together for your...
Yeah, basically sum it together.
Okay, so
Yeah,
you think
yeah, just take summation together. Yeah. Yeah. Okay, so this is the ebook, the section 4.8. So here, if we say k equal to 100, then it will be equal to this, and say k equal to 20. Let me say, this is 100 is here, and then 20 is here. So look at here. Well, it's kind of changing the scale, so this is the scale, and then we go to 20. The scale is the same, so if we go to 10, so from here would be give you a certain idea. If I go to 100, oh, 1,000, so I think I'm wrong. In this case, if we put a k very large, basically you can see the influence from the disturbance get very insignificant. Okay, but however, the input, the response to input, the command input get overshooted too much. Okay, so if you don't like this overshoot, if you wish to reduce the overshoot, then we can try a little smaller. Okay, so even smaller. So you can see if we try the very small number of k, we don't have any overshoot. The system is basically smoothly rising to certain value, but here we have a steady state error here, and here I can approximate about 10%. But also at that low value, we also magnify the influence of the disturbance. Can you see it? So from here, this kind of the plotting and can give us very quick feeling how to know learn how to tune the value of the k. So this is one quick example here. Basically, this is the controller design. And right now I'm showing here for this controller design, you simply pick a appropriate number of the k to fit in your design criteria. Your design criteria could be this. Say, I want the overshoot less than 20%, and I want the system to rise. You can see for this case, the system rise to 1, and that is at here. The system response rise to 1, which is to reach to our command value at 0.1 second. Okay, then we compare to 10. The system rise to the command value, which is about 0.21 second, slower. So in this way, you can design your system, say, I want my overshoot, the system overshoot less than 20%. I wish the system rising time, for example, say less than 0.1 second, and say I wish my system steady state error equal to 0, and I wish my system to be cheap, and anything you put into your design criteria, and then you can, against those criteria, you can begin to tune the k. Okay, and more criteria, more demanding in your design criteria than more expensive in the controller design. For this simple example, you can see just for those criteria I mentioned, by simply tuning the k, we won't be able to reach all the things, all the criteria. We won't be able to meet all the criteria. You can see for lower k, we don't have that overshoot, but we have slow response and we have steady state error. For larger k, we have very quick rising time, but we have a big overshoot and we have a steady state error for 100 and even for other things. So that is the information we obtained, we learned from this tuning.